performance issues that I had promised. So essentially, what are the things to keep in mind when you're trying to program in CUDA? In fact, many of these things are not really CUDA specific, although some of them are. Things that you would want to keep in mind when you're writing parallel programs. Okay. Of course, you'd want to maximize parallelism, right? And from CUDA's point of view, that means as many threads. It also means as many threads in the context of block, non-block breakup, right? Because we know that if there is some synchronization within a block, we can handle it reasonably efficiently. Anytime you require synchronization across the block, either there is some busy wait somewhere which says, is that block done, right? Or you're going to start a new kernel. And so when you're designing your kernels, try to see if all communications or most of the communications can be structured within the block. Okay, and anytime there is this communication, there is got to be some kind of synchronization to ensure that whatever you're sending is actually reaching there. And whenever you can use streams, you should. That's again the issue of maximizing parallelism. They're not necessarily the only way to maximize parallelism, but they're one way. Again, streams are running different kernels, right? So they're not even in the same grid. Not that it would make any difference. Even if you are in the same grid but not in the same block, you have still similar issues to deal with. And so now you have to think about what should go in a block. Maybe I want the entire thing to be one block, because blocks are easy to synchronize. It's possible, right? One thread just does more, and then block size becomes your size of parallelism, right? The amount of parallelism that you get is the number of threads you can put in a block. One problem is that one block has to run on one SM, which means other SMs are idle. You may say, I've got say 16, 30, some odd SMs. I can run 16 kernels in parallel. So I'll run 16 different things, assuming I have 16 different things to do on 16 different SMs. Would you want to do that? Why not? Or why? Sorry? That's one issue. But it's the same amount of work, right? So you may run out of memory on the shared space, but on the GPU, it doesn't matter whether all the threads are organized. So you've organized your parallelism into 1024 threads, right? And they are reading up all the memory. So you were saying that different kernels would be requiring their own blocks of memory. That is potentially one issue. But suppose that's not an issue.
So, but it suits the, let's say if you are an OS, then it's you can run one application per, like one application as a block. So it kind of suits.
As it stands today, only one context can be run at one time. So these different kernels that you can run on different SMs have to come from one context, right? One application. Cannot be from different applications. That may happen, but that requires much more tight interaction between the OS and the device, and which means NVIDIA and Microsoft have to get, or other people have to not merge. Yeah, if they merge, that can happen. But they have to talk very much more closely than they do. That's possible. They don't have to merge to have that happen. As a matter of fact, they've been trying to get that feature in there for at least 6-7 years now. It hasn't happened because they're not the same company. So if they were the same, it would have happened by now. But anyway, since that is not there, what are the other problems? Even if you allowed multiple contexts, suppose there was only your application you wanted to parallelize. That's how we think even in the CPU domain, right? I've got a large amount of computation to do, and let's run it in parallel, not worrying about one user running email application somewhere on one of the cores. So the problem would be that there are only fixed number of threads you can run for a block, right? So 1024, which means fixed number of warps, right? 32 warps, which means if one of these 32 warps is not ready to run in a given clock, then you cannot run. So total number of warps that you have is limited. And you would want many more warps, at least when you're talking about the system-wide number of warps, meaning the total device-wide number of warps, you'd want significantly more than 32 warps to be running. Even on one SM, probably you may want more than 32 warps. All right. So the amount of parallelism that you would get by making one block do everything is going to go down. Or even a small number of blocks do everything. Small number being size of the number of SMs in your system, for example. Okay. So you have to think further by not limiting yourself to saying, I've got k SMs, I'm going to run k blocks, each block is going to do 1/k of the work.
I can say 4k blocks, 4k independent blocks.
Well, that number is not going to remain the same for every kernel, but something, so as a rule of the thumb, something between 4 and 16k is probably a good, somewhere in that range is highly likely that whatever your application is going to have its sweet spot. How that many number of blocks. And then each block does what 1/k of 1/4k or whatever, 10k of the work. So maximizing parallelism is one part of the story. Okay. Now within the code, we've looked at the architecture. Right? There is arithmetic logic unit, right? ALU stuff. There are special function units, which we call SFU. There's fewer of those. You have to run run a warp worth of instruction spread across multiple clock cycles for SFU instructions. And then there are memory instructions. And typically, you would see read from memory, do something on that, then write the result into memory. That would be a natural sequence of instructions you'll find often in any typical program. What does that mean? I read something, and just to give you a sense of, or to put actual numbers here, in fact, I think I have a few numbers in upcoming slide. In fact, let's go there. We'll talk about this difference between different types of instructions and how their distribution matters. Let me go through the last two items, which we will talk about a little later also. The other would be when you do read memory, you know that you're doing parallel reads. Right? You're not saying read the variable x. You're actually saying that thread reads variable x, that thread reads variable x, that thread reads variable x, and 16 of them actually are reading variable x, their own version of variable x. So how do these reads together fetch memory data items, right? Like one capsule of data in an efficient way? What should this pattern be so that you can do this in an efficient way? That's the third thing to think about. And then minimize instructions that take long to run. That is probably shouldn't even be as a fourth item there. But sometimes you can take shortcuts. There are expensive ways to do certain things. There are inexpensive way to do the same thing, probably with some error. And you might make that choice sometimes. This is for 1 point x. Okay. The SFU, for example, can take reciprocal, can do square root, can do log, and it takes 16 cycles to do them. Most instructions will take 4 cycles. Add x to y, multiply x with y, compare, minimum, whatever. But integer division takes significantly more. If you know that, then you would get rid of integer division. Right? In fact, floating point division is much faster than integer division. So you might replace your integer division, if you can, in certain situations, replace it with floating point division.
But you can always reduce floating point to an integer.
Floating point to an integer. What do you mean?
Remove the fractional part. This can be integer part.
So?
We want the other
Convert the integer to floating.
Yeah, so I'm saying that integer division can be done faster.
No.
You can convert it to float and that's what he said.
No. Why not? What is the range of floats? Min float and max float? Much, much bigger than minus 2 to the 32 minus 1 to 2 to the 32 minus 1, right? Or minus 2 to the 32 to 2 to the 32 minus 1. So obviously not all integers will be represented. So you couldn't just do floating point division for integer division. But in certain situations you can. For example, if you know that your integer is floating point representable, then you might do it. So these are the numbers that I was talking about.
So the 4 cycle here, does it mean that the entire walk is going to complete in 4 cycles, or since there are only 8 processing units inside an SM, so does this mean only 8 threads are going to complete in 4 cycles?
These are pipelined. Okay, so every time you can schedule a half warp, it will scheduler thinks that it's done. Half warp is done. Even if there are only 8, as the slide shows, only 8 CUDA cores, 16 warps, 16 threads have been scheduled. Okay. Internally, this hardware has a pipeline, right? So in the given clock, it's going to run 8 of them. Next clock, it's going to run another 8 of them. And so,
each set of them is going to take 4 cycles.
right. So they'll be coming after each other. So 4 cycles later, you're going to get the first. 5 cycles later, you're going to get the second. So scheduling is something that will take 4 clock cycles for most simpler instructions. 32 clock cycles. It has come down significantly. I think it is now 4 clock cycles for 4 or 8 clock cycles for double precision floating point, and then 2.x architecture, and 16 clock cycles for some functions, the ones that go in SFU. And on 2.0, there are 32 CUDA cores, but they are divided into groups of 16, so 2 groups of 16. And as a matter of fact, in in fact, it says here 2.1, it's 3 groups of 16. So it says 48 CUDA cores per SN. There are more special function units in the most recent set of hardware. And there are 2 warps that are being scheduled in the same clock. Which means that since there are 16, a half warp is scheduled at a time. So there are 16, 16, 16. So you can schedule one kernel's one warp here and one other kernel's another warp here. Or one kernel's one block's one warp here and the same kernel's another block's another warp here. The rate at which you can schedule them is also quite much faster. And so that the last statement is probably less of an issue for the most recent set of devices. But the first 3, where you have to think about how to increase your parallelism, how to have memories mix with non-memory, with compute instructions, and what kind of addressing pattern would be good for a given instruction so that all of the memory capsule comes in efficiently. And so those 3 things we are still going to talk about. The other thing that is again something that is reasonably bad for even the newer ones, especially bad for the older architecture, was branch. Okay, which means that if you are branching with some threads in the warp trying to do X and the other threads of the warp trying to do Y, then there is significant overhead for it. Okay. One is that those 2 are X and Y are serialized, but the other is keeping track of which threads are to run when. Okay. All the ifs and else and ifs and else that may be nested require a significant amount of overhead. Now, I said that now you also get this branch predication, where instead of thinking of it as if then do this, else otherwise do that, you think of it as do this and this and this and this, every instruction, with a few of them disabled. And then do this, 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 this and this with every instruction, with a few of them enabled. Okay, it's not good for nesting. Or at least deep nesting, but it doesn't need to do any branch tracking, right? Who has diverged and which of them are converging together. Again, this is something that you have no direct control over. This is part of the PTX instruction, and the language has no way of saying this if condition should be in predicate, although it might make sense for the language to add a macro where you can direct that this instruction should be predicate. Currently, the compiler has some heuristics. If there are small sets of instructions, if within the if and else there are few things that you're doing, then it's going to use predicate. And once it gets complicated enough for it to use predicate, it falls back to the more general branch tracking. Okay. So the message on this slide is, if you can avoid ifs, do so. Okay. It's okay to do if within a warp, in the sense that if all the threads of a warp are true, you pay no cost, you pay no price for it. If all the threads of a warp are false, you pay no price for it. Sometimes you can organize your computation such that, for example, sometimes you want to do something for odd things, something else for the even things. If you do the natural way, you say 0, thread number 0 is handling item number 0, thread number 1 is handling item number 1, then every warp is going to have half odd and half even things. If instead you say, if you are from 0 to block size divided by 2, then you're doing the even things. Block size by 2 to the block size, you're doing the odd things. Right? Assuming no boundary conditions, which you can again arrange properly, either the entire warp will be handling even data item or the odd data item. And so that is not a condition in practical sense. Sometimes it would be also useful to, instead of saying if something, do this, you take the condition code and multiply by results, right? For example, if you want to produce in the result a given variable, if the condition is true, then you can say simply take the condition's result, multiply by the variable and put it in the result, assuming that otherwise you're going to put 0. Okay, so things of that sort typically would be a good idea to do when conditional branching or conditions are inexpensive or expensive. Use shared memory. We've already talked a lot about that. Whenever you can, use shared memory. Whenever you can, don't use sync threads. For example, if you want keep your syncing or this communication as much as possible within your warp, then you don't need to use sync threads.
So the cost of the sync thread?
It is essentially, typically different blocks will be at different stage, right? But if you want everybody to come to the same stage, then whoever has passed that stage becomes not a candidate for scheduling anymore. Okay, so that reduces your working set size, that's all. Okay, now let's talk about the memory organization. Shared memory, I think we have already discussed. These things are in banks of memory, and the address organization is that contiguous addresses go to different banks. Right? So bank 0 will have the address 0 in it, bank 1 will have the address 1 in it, bank 15 will have the address 15 in it, and then 16 will come back here. Okay, and think of this as a memory with 16 ports. Okay, so what that means is that if you're reading from different banks, you can read it in parallel. If you're reading from the same bank, then you have to wait for that data item to come to the port. Okay, and so from the shared memory point of view, if all the different threads on a warp are reading from different banks, you get excellent performance. If they're reading from the same bank, then there will be serialization. So that parallel I/O will become serial, right? It will take as many clock cycles as the number of things coming out of a single bank. Okay, and that number that I was looking for, actually we haven't seen. I thought I had it somewhere. The difference in the number of clock cycles that it takes for data to come from memory versus the number of clock cycles it takes to execute instructions, we have seen that, right? 4 clock cycles is an example of number of cycles to execute an instruction. The number of cycles to get data from memory is 200. And that's the difference. I'm not saying exactly 200, but it's something to the order of 40-50 times. As a result of which, you can do a lot of memory, but this is pipeline, right? It doesn't mean that you say read something from memory and now for 100 clock cycles you can't read anything, or whatever, the 200 clock cycles you can't read anything. You can issue your reads at the rate in which you can launch instructions. It's just that that given reads data item will come back 100, 200 clock cycles later, which means, and there is no branch prediction or advanced scheduling on this device. What that means is, if after that read, you're going to use that data item, you have taken that warp out of the equation for 200 clock cycles. Right? Because until that thing comes, you can't use it. If instead you were to organize your computation in such a way that you read a few things in several different variables, local variables, and then you do the computation on them. What that will do is, because you're reading in independent memory locations into independent shared memory or registers, they can all proceed. There is no dependence among these instructions. At some point, you're going to go and use that variable in which you read something long while back. And hopefully by that time, either the data has arrived or it is about to arrive. So this doesn't get out of commission for a very long period. Okay, so that
Issuing multiple reads and you say issue 10 reads, they are issued in 10 cycles. Then you still wait for 190 cycles.
then you still wait for 190 cycles.
How much?
Not very much if you can only issue 10 reads, right? Remember that you will almost, in fact, guaranteed to never be able to issue 10 reads in 10 clock cycles. Because you don't have the monopoly over the hardware. There are hopefully other warps waiting. So your subsequent reads will probably be spread about 20-25 clock cycles. And so if you made 10 reads, it has taken you about 250 clock cycles to make them. Okay? As long as you have enough warps running. Okay. The memory organization, the global memory, you read data in bulks, right? 256 byte is, for example, an atom size. And you read in a typical application, in a typical instruction, 4 bytes. Right? You say, I'm going to read an integer from memory. I'm going to read a float from memory. Sometimes you can read bigger things. You can read a double. But overall, you're doing 16 such reads. Right? So if you can ensure that your 16 floats, which amount to 64 bytes, come in one atom of 256 bytes, you can get it together. You can get it in single memory instruction. Right? To memory, you say 256 bytes from this address. Okay.
In the absence of caching, what happens to the rest of the 256, 252 bytes if I don't use? In older cards, you don't have cache.
In older cards, so 256 was not the only atom size. You can read it in 64, 128, or 256 bytes. That's the maximum atom size. Okay. So you can, there are 3 different read instructions, or write, and you say, I want to read 64 bytes from that address. That's what the SM will say. And it will say that on behalf of all the threads. Right? So if the thread's entire access comes within one of those atoms, then you get it. Now, because the atom size is 256 bytes, the cache line also is 256 bytes, which is somewhat largish cache line. Because, for example, a typical cache line on a CPU would be something like 64 bytes. Okay? And so, which means fault sharing is something to be especially careful about. The other thing that you want to make sure is that addresses are aligned. Right? So it's not that you can read any 256 bytes. It definitely has to be contiguous. It also has to be aligned at a 256 byte boundary. Okay, and so it's a good idea for your structs also to be aligned. Right? So typically you say read the 10th element of my struct. Right? So for example, in this example, you're saying struct align 16, which means align it to 16 bytes. Float A, B, C, D, E. And so this entire struct will begin at a 16 byte boundary or 16x, whatever that x may be, x being an integer. And you can read the entire struct in one shot. Okay. When you copy a struct to another struct, you can read the entire struct in one shot. So ultimately your coalescing of memory will have to depend on getting contiguous chunks in a single read instruction or a single write instruction. Okay, which means you organize your data structure such that when many things are reading, they're reading contiguously. Okay, let me stop here. Okay, so let's continue. We were talking about performance issues. In particular, we were talking about the memory side of things. And there are two kinds of memory accesses, shared memory and the global memory. And there is different kind of behavior that you want in each. And sometimes those two behaviors conflict, meaning that sometimes you want to bring data from global memory to shared memory. Right? So you copy something from global memory and write something to shared memory, and if you follow the same pattern of accessing, so usually you would say I've got an array and index number I1, I2, I3, I4 are the indexes that the different threads of a given warp, or for that matter a given block, compute, and then they read I1, I2, I3, I4 from the global memory and write at I1, I2, I3, I4 in the shared memory. And that read pattern and this write pattern for you, for the thread, is the same. That would be the natural thing to do. And for example, if you're reading contiguous things, then you would say, I'm reading 0, you're reading 1, you're reading 2, you're reading 3, you're reading 4. And then I'm writing 0 into 0th location, you're writing 1 into first location, and so on. And in some cases, it may be fine to do that pattern for global memory, but not for shared memory. Whereas it may be fine in other cases that you're making the shared memory faster, but not the global memory. Okay, and so then you have to think how to make sure that it is a good pattern for both of them. Okay, and good, so which means you have to understand what is the good pattern for each one of them, and roughly, briefly, what we had talked about is that you want contiguous chunks to be read from global memory, right? So all the threads produce an address, and those addresses are collated into one or more, depending on how those addresses look in terms of contiguity and so forth, into one or two memory accesses. Which reminds me, I had said that the memory atom size is 256 megabytes, which is true for allocation. Right? You allocate in atoms of 256 megabytes, 256 bytes, and the allocation addresses are also aligned at 256 bytes. But you can read at most 128 bytes from memory in one shot. Okay, so that atom size is 128 bytes. You can read less than that if you want. So if you only need 32 bytes, you'll only read 32 bytes. If you only need 64, you'll read 64. If you only need 128, you'll read 128. And if you need more, then you'll send multiple memory transactions. to the memory.
So if you want to read, say, some structure of size 512 bytes, so then 2 threads will be required. I mean, 4 threads will be required. What's the sense?
So let me understand. You're asking, I want 512 bytes of data to come from global memory to shared memory, right? It depends on how you want to read it, right? If those 512 bytes of data are in one contiguous location in global memory, right? Then you know you can read it in 4 memory transactions.
So what does it mean? I mean, by 4 memory transactions, there will be 4 threads, or the same thread will be.
That's up to you. So the hardware says that there are 2 parts to this story actually. One is, think of it as a bunch of processors, which is for us a bunch of threads, producing a bunch of addresses, right? And with each address there is a certain size, right? I may want to read 1 byte at given address, I may want to read 1 int, I may want to read a double. And so how much can I read in 1 instruction is one part of this, one side of the story, okay? And as it suggests here, you can read 32 bits, 64 bits, or 128 bits in a single instruction, okay? Now, there are up to 32 things making either 32-bit or 64-bit or 128-bit requests.
You mean
A warp, right? In 1.x, you are guaranteed that it will be half a warp, because half a warp was running, and then, in fact, a warp was run over 4 cycles, because there were only 8 of them, right? And it was grouped in groups of half warps because 16 requests could go to the memory in one shot, or 16 requests could be collated into one request, one or more requests. In 2.x, that's not necessarily the case, because 2 half warps can be scheduled at the same time, and so it may be all 32. But so, ignoring those kinds of details, so there is a warp worth of read to happen, right? And either it's half warp or full warp, whatever it is. Each instruction, so each instruction meaning one instruction, right? The entire warp has one instruction. That instruction says read 32 bits, or it may say read 128 bits, right? So you can actually read a vector of x, y, z, w. You can see where this is coming from, right? It's all started with graphics, where things always go in groups of 3 or 4, and that's why you can read 4 things in one shot. There's one instruction. In CPU, typically you will have one instruction to read 132-bit data. Here you have one instruction to read 4 32 bits of data. So it's a vector read. One vector read per lane, right? There are 32 lanes, and so 32 people are saying one vector for me, one vector for me, one vector for me, one vector for me. So there are 32 vectors to be read. So now when you think of that single instruction's overall effect, then we are reading 32 times 4 bytes, right? And now the question is, how much can be read in one shot from the memory? That's how much threads want to read. And think of now having a kind of a go-between, where threads say, I want to read, and go-between says, you want this, you want this, you want this, I'll take your orders, I'll combine those orders, and I'll send the minimum number of orders necessary to the memory. So if everybody is reading contiguous blocks, then I can say, you want 32 bits, you want 32 bits, you want 32 bits. So total, there are 16 people wanting 32 bits, right? So how many, 4 bytes, so 64 bytes to be read. And I'm going to send one 64-byte request to the memory, okay? Similarly, if entire 32-bit wide warp wants to read 1 each, right, then it's 32 times 4 bytes. And so I can send all of that in one memory request, as long as those 128 bytes that are being read in the combined warp are 128 byte aligned, and of course the size is 128 bytes. Question.
So, but how this, all this and memory banking that we mentioned last lecture, how does they fit in? I mean, you said banking is like 0th.
So here we so far we are discussing from the global memories perspective. Okay, some of the discussion remains the same. Even when you're doing shared memory, you are saying all of these people want to read something, and for a given warp, there are so many orders from the global memory. You collate those orders, and then you decide to place those orders with the memory.
For banking, I mean,
Right.
we have different banks that can read, issue reads in parallel, right?
Right.
So how does, because right now what we said is the optimization is only one single memory instruction, memory access instruction to do the whole 128 byte, okay? And but the banking says if you divide it into different banks, then you will be having faster results. So how does this balance?
How do those two balances? So first of all, there are banks even in the global memory side, but they're transparent, so they're not made visible to the programming model. Banks in the shared memory is actually made visible to the programming model. That's one. Okay. Second, but the more important thing is the banking is related to how you address them. I said I want to read address 0, the next thread wants to read address 1, the next thread wants to read address 2, and the 16 threads want to read addresses 0 to 50. So when I combine those orders, I'll say I want to read 16 bytes starting at 0. Right? Now, if the banks are visible to me, then I'll say, where does the address 0 reside? Resides in bank number 0. Where does address 1 reside? Resides in bank number 1. And address 15 resides in bank number 15. So now if I have to say, I want to read 16 things, 16 ints, starting at address number 0, what does that amount to? It amounts to reading one address 0 of each bank. Right? So as long as your addresses are striped through the different banks, right? You go 0, 1, 2, 3, 4, whatever the bank size is, and then start again. Then contiguous addresses will come from different banks. As long as they are aligned.
And this we still call this as single memory instruction. Even if
Yes, it is definitely a single memory instruction. Yeah. From the program's point of view, it is a single instruction because everybody is saying read a given address. It's a single read instruction. They all have different addresses to read, but that's how SIMD works. And from this waiter point of view, who's taking everybody's order and feeding it to the memory, it is still a single memory instruction because it's saying read 16 bytes starting at 0. The addresses are so assigned that they're coming from different banks. Okay. So in this example here, what you're seeing is at the top example, we have some type and we have an array of that certain type, and you can say data is equal to device a given array location, right? My TID. And this is again, we are, as the slide says, talking about global memory organization. That will amount to a single instruction. Different TIDs will be accessing different addresses, but everybody is saying read something. Read something at a given offset from the device. And in this case, because you're using directly TID, those offsets are contiguous. Because all the TIDs are contiguous. Now depends on the size of type. The size of type is 4, 8 or 16. We get 32, 64 or 128-bit instructions.
So what is the sense of contiguity in TIDs? I mean contiguous processors or something like that?
The thread IDs that you have within a warp are contiguous.
So they are launched by contiguous SPs.
You don't directly see the ID of SPs. Okay, they're launched by all the SPs. It is possible that some of the threads are not actually executing this instruction, right? Because they have diverged. There's an if condition, or there's a predicate that has disabled that specific lane. But processor, you never really think in terms of processor ID. It's a thread's ID. And you know that for a given warp, thread IDs will be contiguous. It won't go from 0 to 16, warp size is 32, 0 to 31. But it will go from some 32x to 32x plus 1 minus 1, where x plus 1 is in parentheses.
Why do we have a notion of a warp which is separate from a notion of a block? Why don't we just do away with the notion of the block and just keep warps in
Then your blocks become really small. No, because you can actually have a much more friendly relationship with other warps of your block than you do with warps in the same kernel but not in your block, right? So you can do more synchronization, you can share more data, you share the shared memory. All of that will go away, right? Because then it's a very small size. Okay, so now looking at the other example where it's struct which has been aligned to 16 bytes, meaning that it's going to take aligned 16 byte address, and you say x equal to y, and that x is 5? Yeah, 5 floats. It can be, by the compiler, it will be compiled into 2 instructions. A, B, C, and D will fit in one instruction. So it's going to read A, B, C, and D in one instruction and E in the other instruction, and copy it from X to Y. So instead of making 5 float loads, it's going to make one vector load of float 4 and another float 32-bit load. Okay, so coalescing is happening at that level. As we discussed, memory transactions will be one of these sizes, 32, 64, or 128 bytes. And if all the instructions addresses fit in one of these, good. It's going to take a single instruction. If they don't, then multiple instructions may be required, right? For example, if the first address is 0 and the second address is 5 and the third address is take multiples of 5, right? What is going to happen for global memory read? So you're reading 0, 5, 15, 20 and so on.
As many instructions.
Because the waiter is not going to be able to put them all on one plate, it's going to send them all in their own individual plates. Right? It is going to combine the things it can, it's going to leave the rest as their own instructions. And nowadays, meaning with 2.x, anytime it can combine them, it does. Especially in the 1.0, 1.1 time frame, there are a lot more restrictions in that they had to be uniformly spread and they all had to be aligned, and no two of them might be reading the same address. So there are some unnecessary restrictions that have since been removed. So it would behave in an expected way as long as you are sending addresses that can be coalesced.
It's only addresses within a block that are coalesced, or everything that is running on that SP can be coalesced?
There is nothing like everything running on that SP, right? Because it is done at an instruction by instruction basis. When one instruction is run and it has to come from half a warp, right? It's only that instruction's addresses that are being coalesced, because anything else comes in next clock cycle, whenever that is going to be scheduled. And in fact, I didn't I was looking for the numbers about how fast things run, and I put in a slide in the end when we are going to review these things about how fast the different instructions run. So there is a coalescing algorithm, which I'm not going to go through. It's basically whatever we talked about is what it implements. It looks for addresses that can be combined together, and it combines them. And there's still, even in 2.x, there are certain situations in which weird distribution of addresses will not be combined. For example, some later lane reading a previous address, previous lane reading a later address, and some other lane in the middle reading something far away. Okay. So the same set of rules are also being demonstrated in this, where you are reading two different locations in this struct called device. You first read device 1, and this stays in global memory, and then you read device 2. Okay, you could instead simply read device. What is the difference? And this is again a more concrete example of something that I was hand waving about at the end of last class.
This one is more optimal.
Why?
All the threads will
Struct of
be
array is
moving
not
together.
array.
Don't blindly look at struct of arrays.
Continuous memory.
I mean, that is correct, but one step deeper. Why? No, not all struct of arrays are going to work.
All threads will be reading continuously memory.
So look at the first instruction. Right? Everybody is reading something, right? And they're reading contiguous chunks. Right? If you had read the whole thing, would that still happen?
Keep jumping from here.
Why?
Contiguous.
Why?
In this case, it would.
It will collate all the them together.
What happens when I read it together? In meaning that I say device struct device blah is equal to device is equal to device TID, where you would have to declare it also of that type, right? You'll have to declare as type 1 device, type 1 device 1, type 2 device 2, and the array would be outside. Device of size 32.
So in that case, it would be jumping around, right? Like you said.
But if I take the entire device, right?
Depends if the two fit in together. I mean, if type 1 and type 2 are very big, I mean, like,
If you are accessing complete whole device as a one entity, then that would be better. The one that
Can it be? How big would it be? The whole device would, now the array is outside.
yeah, because then now we have array of devices, which is contiguous.
Right? But will that be one instruction?
Size is 256.
256 byte space boundary.
256 should be the size of one device.
Depends on type 1, type 2. Sir.
Depends on type 1, type 2, right? Suppose type 1, type 2, let's put some names there, int.
Then multiple device reads can be.
It will coalesce because they're all going to read the entire array. So they're all going to have the same addresses. Why you would do that is not clear, but for some reason everybody needs the same data. Then everybody is sending the same address to be read. And how many are to be read? 32 times 2 integers, right?
Depends on how the compiler will process it. Because let's say that okay, this is a struct which has two integers. First, let me copy the first one to
No, I'm assuming that you can optimize the compiler. I don't want to deal with what the compiler actually does. We talk about what it can do, what it might be able to do. So array assignments can be done in one shot. Right? Struct assignment can be done in one shot. So small static arrays can be done in one shot easily. It doesn't have to open a loop for it. So everybody is reading the same array. Everybody is producing the same address. And the address is starting somewhere, wherever device 0 begins. 32 times 2
into TID or not?
Not TID, right? Because everybody is reading the entire array. Because you have just said type data. Another array is you reading something into local array from the global array.
each one is reading one device, right?
No.
So why is it?
Each are reading TID.
So let it read one device. That is what just reading.
Okay.
Each are reading one item, right?
Sorry?
Collecting all the requests together to get the entire stuff. Because only TID is reading just TID one. It's only their own TID.
Yeah, what sir is saying is each one is reading the whole array.
Yeah, I was saying if you read the whole array, it is the same thing as you reading 0th position, you reading first position, you reading nth position, as long as the compiler recognizes that. Okay, and it will be coalesced, right? It's contiguous, and of course it won't fit in one instruction, but it can be done in two. Right? There is also, if you're making 2D arrays, you want to make sure that your dimensions are multiples of 16, or you use something called pitched malloc, okay, meaning that it is going to pad to each row some number of bytes so that the next row begins at a proper multiple. Depends on the type. Proper means multiple of the atom size, the type size within it. Okay?
So we can go back to the last one.
Yeah.
So if type 1 and type 2 are big things like say 40 bytes, it's 32 bytes each. In that case, what would be a better
16 by 16. Unless
16 is because 16 is linear. No, so if they are larger, then if every thread wants to read its own struct into the memory, then each one starts by reading the top field and then goes further down.
yes,
So that would be inefficient
that would be inefficient.
in that case. But if they were small,
Then if they were small, then it would be perfectly fine because it will fit in one instruction. Okay, so this is, again, I'm not going to dwell on this. It's something that you have to keep in mind if you're going to use 2D arrays. Either your widths, the dimensions of the arrays are going to be multiple of the size. Here it says 16. Right, so basically every half warp will be aligned to 16 times whatever the size of the data is, right? And so the alignment will be in data terms, some multiple of that data aligned with 16 times that, which is exactly where we started with, right? We said that if you're reading blocks of 128 bytes, then it's aligned by 128 bytes, which comes from 16 times the read size of each thread. Or if it is blocks of 64 that you're reading for the entire warp, then 64 comes from 16 times the read element size of each thread, right? So as long as your width is 16 of whatever type you're using, it is going to get aligned. Each of the reads, as long as they're contiguous IDs, contiguous indexes into this array, they're going to get aligned. And so there is this notion of CUDA malloc pitch instead of CUDA malloc, where you tell it what is that alignment, what is my size that I'm going to align. So it takes X as well as Y dimensions and then gives you data that is expanded so that the alignment can be taken care of. And then you have to also access it in a certain fashion. Right? Malloc pitch simply is a malloc with a slightly bigger size, aligned size, so that if you're not using the entire width, you can leave a little bit of buffer on the right hand side. And there are ways of reading data from the malloc pitch in a standard way. Okay. So in this case, you are saying I am going to read in multiples of this pitch, okay, and you provide that pitch to the reader, which is going to access it. Right? So pitch is something that is being returned by CUDA malloc pitch, and in the reader, you, depending on how many rows you have crossed, you are saying you need to offset your address by that many pitch multiples, because every time you go to the next row, there is pitch worth of data that that is blank, right? That's buffer. So you have to skip across that. On the shared memory side, it is still contiguous that you like, right? Addresses should be contiguous. What about the differences I was saying that shared memory and global memory have? How does that make a difference? When would a contiguous read from, so you're saying I need to bring a block of data from global memory to shared memory, and as a thread, I'm going to read this block and I'm going to write that block, same block, into the shared memory. When would it not work well? I'm ensuring that it's contiguous on both sides. When would it not work well? Meaning one of them is not getting accessed in a coalesced way. Think about it.
I mean, you want a situation wherein we can do more with the structure by knowing the structure of the shared memory? Is that clear?
No, we know the structure of the shared memory. I'm asking you the question, if I'm simply taking a block of data from global memory and saving it in the shared memory, where is an example where, and both of them are contiguous, right? I'm taking a contiguous block from global memory and saving it contiguously in shared memory. Where is an example where I'm not accessing the memory in coalesced fashion? And I'm going to stop